Maybe I shouldn't be playing final boss music right before break. That gives the wrong impression, huh? Don't panic, there is no test. Not today. Alright, I don't see Axel or Christian in yet. No? Okay. Alright, then good morning, everybody. Let's get started. We've got one final lesson before you take off for Thanksgiving. Okay, and it's a bit more involved, but I hope it's fairly straightforward conceptually for you. And that is, well, okay, we'll go over the triangle inequalities, but the new thing for today will be similar triangles. Talk about inequality. This is inequality between triangles, comparing two different triangles. Okay, so before we get to that, yes, please go ahead and open up yesterday's work. Let's run through the answers to those questions real quick. So first up, is it possible to make the following triangles? First one, yes, those numbers all fit together. Second one, no, that 28, way too big. It is bigger than 9 and 17 put together. So you end up with a scrawny little thing that can't quite fit. Question number 3 gives you two sides and says, what's the range on the third side? Okay, so you need to think about this as, what are the extreme possibilities here? The biggest it could possibly be would be if I added these two together. Right, 17 plus 36 would be 53. We said we're not allowed to be bigger than the sum of those two. But what if the third side isn't the biggest? What if the third side is actually smaller? So then that leaves the bigger of these two, the 36 would end up being the biggest side. And so then 36 can't be any bigger than 17 plus something else. So you take 36 minus 17 and get the 19. That's your low end. So it has to be between those two numbers. Any questions there? All right, then. Arranging the unknown measures. So here we go. Number 4. Biggest to smallest, greatest to least, B, then A, then C. 5, B, then C, then A. And number 6, oh, it gets tricky here. We've got overlapping. Here's a triangle. Here's a triangle. Okay. A could be part of a triangle there. A could be part of this triangle here. All right, so make use of those overlapping triangles. These things share sides there. So based on the measurements given, we know A has to be bigger than C. And C actually ends up the same size as D, which has to be bigger than B. Okay, so you look within a given triangle where those two sides compare to each other compared to the known angle lengths, right? All right, 7 and 8. Find the missing measurement here. Okay. This makes use of a little thing we call the exterior angle conjecture, which is a shortcut, if you will. I know this triangle, the 3 angles in here, include this guy right here that's unmarked, add to 180. I also know that this guy plus the 142, being a linear pair, will add to 180. And you combine those two facts and you get what they call the exterior angle conjecture, which is a shortcut between the two that just says an exterior angle on a triangle like this will be equal to the sum of the non-adjacent interior angles. So from there, we can jump to say x plus 66 equals 142. That's kind of a nice little shortcut there. But not something you couldn't have figured out the long way. Same with this one, although it's isosceles, so we know those are going to be the same. Find x equals to 79 there. Number 9, what's wrong with this picture? We've got lots of things wrong with this picture, right? This is 120, so then its linear pair over here, CAB, this angle, would be 60 degrees. And this angle here, ABC, inside there, would be 180 minus 160, 20 degrees by linear pair. But that gives us 60, 90, and 20. And that does not add up to 180 degrees, as it should in a triangle. So something is fishy. One of these numbers is wrong. Or this is wrong, right? This is not actually a right angle. Could be any of those. Okay. Any questions on those? All right, then number 10. Again, making use of that exterior angle conjecture. This is just the shortest version. Again, if you're not invoking this idea, then you would be going the long way around and saying, well, okay, these two angles plus this third angle have to add to 180, and this third angle plus the 2x has to add to 180. So you can subtract 180 from both, like set them equal to each other and subtract and get down to x plus this thing has to equal 2x. You get that equation. Subtract x from both sides. So PQS, that angle measure has to also be x. Means they match on both ends there. And that has to do with the isosceles triangle. The proper term is the isosceles triangle conjecture converse. Because the conjecture itself said if it's isosceles, then the base angles are congruent. So we're going backwards. If the base angles were congruent, then it must be isosceles. Okay? And again, using these statements, these are just shorthand. That's all it is. We've condensed a whole statement of fact down into a few words because we're mathematicians and we're lazy. We want to write out as little as possible. You can, of course, write more explaining what this conjecture is. But having these list of references to just invoke, oh, that's triangle sum conjecture. Oh, that's isosceles triangle conjecture. That's just a convenient shortcut that we can use to communicate between us back and forth. It's a secret language that the English folks won't understand. All right, any questions there? No? You're good to go? All right, then let's hit this last triangle feature of the quarter. Yeah, because after break we come back and we deal with circles. So here it is, the similar triangles. Similarity, by definition, means if two things are similar to each other, that means they have the same shape, but they are different sizes. Okay? Now my question then becomes, well, how does that compare to congruent? Congruent, we said, means the same shape and same size. Exactly the same, identical. Whereas similar means we've taken one and we've scaled it up, right? We've zoomed in, or maybe zoomed out. You could scale it down, make it smaller. We've shrunk it without changing it in any other way. Okay? So as a result, your similar triangles, the corresponding angles are congruent. Okay? How far rotated the sides are to each other, that doesn't stay. That doesn't change. That stays set when you stretch and shrink it. But the corresponding sides are proportional. Okay? And this is why your study.com lessons this week start with proportions, right? Setting up a proportions. To say that two things are proportional, you are setting one fraction equal to, let's not repeat the two. to another, right? These two ratios are equal, so they are proportional to each other. So if you were to compare the two sides of a triangle, the left side versus the right side of this triangle, and the other triangle has the left side and the right side in the same ratio, right? The relationship between 1 and 2 is the same as the relationship between 3 and 6. It's twice as big. Okay? So if this side is twice as big as that side is twice as big as the other. Also, you can look horizontally across and say, what did I say, left and right? The left side of the big triangle is 3 times as big as the left side of the small triangle, and the right side is 3 times as big as the right side of the small one. Okay? That should always be the case. Okay? When you go from one triangle to the other, you should be multiplying by the same thing, as long as you're matching the corresponding sides. And that's something that you'll either have to look at and figure out, okay, this one matches up with that one based on the order they're in, or if they list them for you. Remember, there's a reason we write everything in order. Take a look at this example. Triangle ABC in that order. Single squiggle. There's your symbol for is similar to. Okay, so we had the fancy symbol for congruent. It was equals but extra. This is similar. It's even reduced. If you see, sometimes you might have seen the tilde like about 7. Not quite 7, but close to 7. We rounded it. Right? So same symbol. Right? Or similar to. It's pretty close, but it's not exactly the same. Triangle XYZ. And because they're in this order, we can know that vertex A corresponds with vertex X, vertex B corresponds to Y, and C corresponds to Z. And we want to find the missing lengths Y and Z here. Okay, so I know my lengths in the small triangle. I don't know the lengths of the large triangle, except one of them. I've got the hypotenuse measured already. So I need to set up a proportion. If I want to solve for, say, side XY, right? That would be side Z. How does that compare to its corresponding side in the small triangle? Right? Well, that comparison is exactly the same as the comparison between the hypotenuses, the two measurements I do have. So just make sure you're setting things up in the same position. If you set large triangle on top of small triangle, as I've done here, make sure the other side is large triangle on top of small triangle. That'll work. There's an equation. Solve that for Z. Okay, I need the Z by itself, so I'm just going to multiply both sides by 5. Right? That reduces there. And then Z is 19.5 divided by 13, then times 5. Why did I cross out that 5? I'm not sure. I got cross out happy. Anyways, right? So you can run that in a calculator. I happen to know, because I set up this problem, that 19.5 divided by 13 is actually 1.5. So it's 1.5 times bigger. Right, so 1.5 times 5 would be 5 plus half itself. Half of 5 is 2.5. 5 plus 2.5, 7.5. Any questions on how I did that? No? Okay. Alternatively, right, let's try setting up to find Y. Let's go the other way. Instead of big on top of small, let's put Y on top of the known one. So we'll make a single ratio within our triangle, Y over 19.5. Okay, now I've got to set up corresponding sides. I need y is side between x and z, x to z. Okay, so the corresponding vertices would be a to c. So from a to c, we can definitely be sure based on the given information, not just what it looks like in the picture. I think it goes here. What if they spun this around and rotated it, flipped it around on you? Okay. We haven't calculated y. We don't know yet that it's going to be larger than z and smaller than the hypotenuse. Okay, we don't quite have that information guaranteed yet. So go with what we do have guaranteed. The given information is which sides correspond with which. Okay, across from b is 12, across from y is y. So this should be the side 12 over the 13 there. All right, and now when I do it this way, I can again look at, all right, well, what is from one triangle to the other? I prefer this method because I like to think of how much bigger is the triangle. What is the scale factor there? Okay, this is times 1.5. Okay, that's my scale factor. How much bigger the other triangle is than the other, which means this has to be a matching scale factor. So I don't need to deal with solving the equation and all this. I just know, oh, this is times 1.5, so this needs to be times 1.5. So I'm just going to take 12 times 1.5. Half of 12 is 6. 12 plus 6 is 18. That's my answer. Any questions on how I did that? No? All right. You guys are either brilliant or so confused you've been stunned into silence. I can't tell which. Let's put that to the test. Let's see how much you know. All right. Here's a fantastic, very common application of similar triangles, and that is using casted shadows to measure the heights of things that are otherwise impractical to measure. Okay? For example, if you want to know the height of this tree, it'd be kind of difficult. You'd have to get some kind of a ladder, and with the leaves, it's like, okay, exactly how high do I measure it? Where do I measure to? And climbing up there, you'd end up out here, and you got to lean into the middle. It's over there. Like, you can't reach it, right? Up your tape measure, impractical. But when the sun is shining, it comes through and it casts a shadow at the same angle on everything, including you. So if you line yourself up and you know your height, you've measured it, you've been to the doctors, they gave you a measure and said, hey, you're 5 feet, whatever inches. Right? For this example, let's go with 5 feet exactly. And you walk over to your shadow, lines up with the tip of the tree's shadow. What you have is this diagram of a triangle on top of a similar triangle. They're both 90 degrees. The tree and you are perpendicular to the ground. And they both share this angle here. Okay? And we know triangle sum, if they share two angles, they've got to share the third one. So these angles have to match. Okay? All the angles are congruent. Okay? We have similar triangles. So let's assume that these sides are all in proportion. Go ahead and solve for that height h for me. And then send me your answer in chat. We'll give you a little bit of a hint here. This 10 is that much. It's how far away you are from the tree, and 7 is from you to the end of the shadows. Which means the big triangle has a side length of the sum of those. That was enough. They still there? Everybody left to go get lunch early. They've abandoned me. I knew this was a bad idea. I'm just out here speaking to the wind. Yeah, I mean, it's their homework. They're gonna have to do it eventually. No one has an answer yet? They really did leave for break early. My goodness. Well, anyone still watching the YouTube video later? A quick reminder then on the actual practice exercises for today. Similar triangles right here. So you've got the book loves these kinds of setups where you've got crisscrossing triangles connected to each other, right? And it really is a nice setup because you automatically get these two vertical angles. So those have to be the same, and it's kind of neat there. So you make use of that, and so realize that this triangle is like flipped around compared to this one. So T corresponds with M, right? And then C corresponds with R. Okay, so don't let that confuse you too much. But otherwise, these are fairly straightforward. You've got 5 and 6 here, right? Deal with The triangles on top of one another. Oh, so does that one there. So similar to the tree setup. All right. And 8 relies on a property of circles that we haven't gotten to yet because we're doing circles next week. So for now, go ahead and skip number 8. All right. Unless you feel so enthralled, like I really want to take on this challenge, can you find the appropriate circle property in the big fat notebook and apply it here? So I'll be impressed if you can do it. But yeah, go ahead and give that a skip for now. All right. Oh, looks like we finally got an answer. Okay. Eddie is still here at least. 12.4, he says. That's fairly close to what I got. 12 point something. I think your rounding is a little off there. So we could set this up again any number of ways. I'm trying to find the height h. Let's start with that. H compared to this total length is 17 is going to be the same as 5 over 7. Those will be the same ratio. So from 7 to 17 is the same as from 5 to h. So whatever I multiply by, so 17 divided by 7, which was 2.4285. We'll take that times 5. Or treat this as an algebraic equation and just solve for h. So we're going to multiply both sides by 17. And so you have the same setup here. 17 divided by 7, multiplied by 5. Okay, order multiplication and division are in the same order, same level on order of operations. So that doesn't make a difference. And you get about 12.143. I'll round to 3 decimal places for you. All right. There you go. If you got 12.143, you know what you're doing. Carry on with the rest of the page. If you did not get 12.143, you've got some more studying to do. You're going to need this practice. So if you have any questions, please let me know. I'm happy to help. But I think we're going to stop the YouTube stream there. I'll put the music back on and let you work for the rest of the period. Okay?